Supercomputers are among humanity's most vital instruments, driving scientific breakthroughs and expanding the frontiers of knowledge. At NVIDIA, our journey has been profoundly shaped by our work on supercomputers. In 2006, we announced CUDA and launched the world's first GPU for scientific computing. Japan's Tokyo Tech Tsubame in 2008 was the world's first NVIDIA accelerated supercomputer. 4 years later, NVIDIA powered the world's fastest supercomputer, the Oak Ridge National Labs Titan. Then, in 2016, NVIDIA introduced the first AI supercomputer, DGX-1, which I hand-delivered to OpenAI. From the world's first GPU for supercomputers to now building AI supercomputers for the world, our journey in supercomputing over the past 18 years has shaped the NVIDIA of today. Since CUDA's inception, NVIDIA has driven down the cost of computing by 1,000,000-fold. For some, NVIDIA is a computational microscope, allowing them to see the impossibly small. For others, it's a telescope, exploring the unimaginably distant. And for many, it's a time machine, letting them do their life's work within their lifetime. NVIDIA CUDA has become one of the very few ubiquitous computing platforms. But the real stars are the CUDA-X libraries. They're the engines of accelerated computing. Just as OpenGL is the API that connects computer graphics to accelerators, CUDA-X are domain-specific libraries that connect new applications to NVIDIA acceleration. CUDA-X opens new markets and industries to NVIDIA, from healthcare and telecommunication to manufacturing and transportation. In chip manufacturing, cuLitho accelerates computational lithography. In telecommunications, Aerial processes wireless radio on CUDA. And in healthcare and genomics, Parabricks accelerates gene sequence alignment and variant calling. For data science and analytics, cuDF supercharges data processing, accelerate popular libraries like SQL, Pandas, Polars, and Spark. cuVS accelerates vector database indexing and retrieval, central to building AI agents. NVIDIA cuQuantum Library performs quantum circuit simulations on CUDA. Omniverse is a suite of libraries that realize and operate digital twins for robotics, manufacturing, and logistics. This week, we announced a major new library, cuPy-Numeric, a GPU-accelerated implementation of NumPy, the most widely used library for data science, machine learning, and numerical computing. With over 400 CUDA-X libraries, NVIDIA accelerates important applications in nearly every field of science and industry, fueling a virtuous cycle of increasing GPU adoption, increasing ecosystem partners, and increasing developers. One of our most impactful libraries is cuDNN, which processes deep learning and neural network operations. cuDNN accelerates deep learning frameworks, enabling an incredible 1,000,000-fold scaling of large language models over the past decade, and led to the creation of ChatGPT. AI has arrived, and a new computing era has begun. Every layer of the computing stack has been reinvented, from coding software with rules and logic, to machine learning of patterns and relationships, from code that runs on CPUs to neural network processed by GPUs. AI emerged from our innovations in scientific computing, and now science is leveraging AI to supercharge the scientific method. I spoke about this fusion in my Supercomputing 2018 address. Since then, AI and machine learning have been integrated into nearly every field of science. AI is helping to analyze data at incredible scales, accelerate simulations, control experiments in real time, and build predictive models that revolutionize fields from drug discovery, genomics, to quantum computing. Using AI, we can emulate physical processes at a scale previously computationally prohibitive. This transformative impact has been recognized at the highest levels. Geoffrey Hinton and John Hopfield received the Nobel Prize in Physics for their pioneering work on neural networks. Demis Hassabis, John Jumper, and David Baker received the Nobel Prize in Chemistry for groundbreaking advancements in protein prediction. This is just the beginning. Scaling laws have shown predictable improvements in AI model performance as they scale with model size, data, and computing power. The industry's current trajectory scales computing power fourfold annually, projecting a million-fold increase over a decade. For comparison, Moore's law achieved a 100-fold increase per decade. These scaling laws apply not only to LLM training, but with the advent of OpenAI Strawberry, also to inference. Over the next decade, we will accelerate our roadmap to keep pace with training and inference scaling demands, and to discover the next plateaus of intelligence. This is Blackwell. Today's AI computers are unlike anything built before. Every stage of AI computing, from data processing to training to inference, challenges every component, from GPUs to memory to networking and switches. The significant investment in AI factories make every detail crucial. Time to first train, reliability, utilization, power efficiency, token generation throughput, and responsiveness. NVIDIA embraces extreme co-design, optimizing every layer, from chips and systems to software and algorithms. The Blackwell system integrates 7 different types of chips. Each liquid-cooled rack is 120 kilowatts, 3,000 pounds, consists of 18 compute trays, 9 NVLink switches, connecting 144 Blackwell chips over 2 miles of NVLink copper cabling into one giant virtual GPU with 1.44 AI exaflops. Incredible.